Tiny structure editors for low prices, generating GUIs from toString functions. So here's an example of what we're doing. On the top is a value of interest, and then I wrote a toString function that turns that value into this string output here. So we can see that this value represents an interval on the number line from -infinity up to 10. And then recall that the square bracket here means that the 10 is included in the interval. Right? So our system automatically turns this output into an editor that lets you manipulate the original value. So I can click this little button here to swap this Boolean in the original value of interest to say, oh yeah, the 10 is or is not included in the interval, right? So that's what we're doing. But why would anybody want a system like this? Well, there are systems like Python Tutor that take your program's internal data values and visualize them. We'd like to take this a step further and make those values manipulable, and you can manipulate those values to change your code. But every program has custom types. So how do we make manipulable displays for the programmer's custom types? Right? So we could show a pointer graph like Python Tutor does, or maybe some generic text, and that wouldn't be too hard to make manipulable. Ideally, the programmer would be able to make their own custom visualization, like this interval on the number line here. But are we going to force them to learn a new GUI framework just to make that manipulable? That seems like a lot to ask. Well, programmers already write toString functions. Maybe we can take their toString function and automatically turn that into an editor. So that's the approach that we're taking here. Now, there are a couple of systems that let you change strings in the output of a program, and they can backpropagate those changes to strings in the input, but they only backpropagate to strings in the input. We need to be able to do this for any value of interest. So what we're going to do is we're going to use a generic dependency tracing scheme. And we found that transparent ML, TML by Ajar et al., works for us. It's their dependency provenance scheme, right? And then the second thing we need to make this work is we need to keep track of substrings. So the way we do that is we are going to defer string concatenation. So normally string concatenation produces a new flattened string. Instead, we just produce a data structure that remembers the string concatenations. Right? So if you put this all together, we start with our value of interest. We tag all the subvalues with unique identifiers. We call toString on that value, and it produces a deferred concatenation, which can be equivalently viewed as a tree. And transparent ML propagated all the dependencies so we know which substrings relate to the original value of interest. So we can see that the square bracket here at the end is dependent on the identifier 2.2.bullet. 2.2.bullet is the Boolean here. Right? We can take this information and now we can overlay nested spatial regions on top of the toString output. In practice, these regions are flush. And turning that into an editor, we can now select 4 of the original subvalues in the original value of interest. And for some of those subvalues, we can draw a little button to swap the variance. So here it is in action again. I can click the little swap variant button to change the Boolean true to false. But we can also swap the variant for the entire ending boundary. So we can change it to an infinite boundary, like so, or we could change it back. We can also edit the numbers as well. Here's an example for a list. You can see the toString output for the list is cleaner than the programmatic representation. Here I'm showing that you can select all the different sublists. And for lists, we are also able to render insert and remove buttons, like so, to insert and remove elements, or remove an element there. And these insert and remove buttons are based on the types structure here. All right, now to assess these editors, we wrote a bunch of toString functions for various data types. And then to provide some evidence that this can work on unmodified toString functions, we translated some functions straight from Haskell. We measured how many of the subvalues of the value could be uniquely selected. So there's some place to click to select that unique subvalue. The results were mixed for our own data structures, but for the Haskell data structures, you could select any subvalue you liked. More importantly, for the data structures that are containers that contain elements, we also measured how many of the contained elements could be uniquely selected, and you can always select the element you want. So that's good. Right? The biggest limitation is that we didn't build this as part of a larger system, so there's still a lot of questions about how it might work in practice. And then right now there are certain subvalues that you can't select because they're being covered up by other subvalues. So the 10 and the bracket here are covering up this entire end value here. And finally, the automatically generated insert and remove buttons only work well for list-like data structures and not for trees. So that's tiny structure editors for low prices. We use generic dependency tracing and deferred string concatenation to generate these tiny structure editors from toString functions. And that allows custom manipulable visualizations for programmer-defined types. Thank you for listening, and I'm happy to take any questions.